Hello, AP Chemistry students. This is Mrs. Altman. We are on video number 40, Thermodynamics Part 2. Here are our objectives with today's video. Pause here. So if you didn't already know the laws of thermodynamics, these are just things that are really useful to know to aid in your understanding. You're almost never directly asked about these things, but if you understand those things, a lot of the other logical principles follow. The first we all know pretty well, energy is conserved. That's why we can assume that the amount of heat transferred from one object is the same as the amount of heat received by the other object, like all of the the calorimeter experiments we did at the beginning of the year. The second, the total entropy of the universe is always increasing. That kind of just helps us to understand why processes that have an increase in entropy are more likely to be spontaneous. And then the third, which really will not come up, the entropy of a perfect crystal at absolute zero is zero because the natural log of one is zero. There's also a sort of zeroth rule of thermodynamics as well, but don't worry about that. Pause here. Now, this equation right here is really, really important and is one that you're going to end up memorizing, just like PV is equal to nRT. So Gibbs free energy, or sometimes you're going to hear it called free energy. It's the measure of thermodynamic favorability of a process. It doesn't really have any physical meaning, but knowing if something is going to be spontaneous or not is hugely important. If delta G is negative, the process is spontaneous, and if it is positive, the process is not spontaneous. So you're going to see in this relationship that delta H, T, and delta S all play a role in whether something or not is going to be spontaneous. Pause here. I'm going to show you how I like to think about these things. There's totally a bunch of ways to do this, but this is how I like to do it. So I'm thinking it's like an XY axis where my Y axis is my G and my X axis is my T. So according to that equation, H is like my Y intercept. So my Y intercept is going to be positive, and then delta S is positive. So that means it's going to go like this. So for the first one, this is spontaneous at high temperatures. Right, so I'm making my plot again. Delta H is negative, and then delta S is negative. But keep in mind there's the negative before the negative T delta S. So this is spontaneous at low temperatures. Right, so my delta H is negative and my delta S is positive. So this is spontaneous at all temperatures. And then this, my delta S is positive and my delta H is positive and my delta S is negative. So this is never spontaneous under any conditions. Pause here. So I'm not going to really get into the calculations in this video because this is something that we're going to do more in class, and it's really, really similar to the delta H calculations. So if you have a table of values, we can actually apply both Hess's law here, and we can use standard free enthalpy changes. So everything that worked with enthalpy also works with Gibbs free energy, also works with entropy. Pause here. So everything that applied to delta H also works here. It's products minus reactants, and you use the coefficients in your calculation. You're never going to need to change the sign for any of these. They're already going to be factored into it. So the calculations are typically pretty straightforward. Pause here. You could just do a rough sketch of the picture. Right. So if you take a look at the equation, the delta G is equal to negative RT ln K, and that R is 8.314, not the 0.083206. So if you're looking here, it actually forms the equilibrium point is going to be the point that minimizes G. So there's going to be a point where